Introduction. The search for life beyond Earth is a quest as old as human curiosity itself. For most of history, it was an exercise in speculation and imagination, constrained by the limitations of observation and knowledge. Today, thanks to advances in astronomy, planetary science, and technology, the exploration of habitable worlds beyond our solar system has become one of the most dynamic and rapidly advancing fields in science. Central to this exploration is the identification and study of exoplanets, planets orbiting stars other than the Sun, and in particular, those that reside within their star's habitable zone, HZ, where conditions may be suitable for life as we know it. The discovery of the first exoplanet in the 1990s marked the dawn of a new era in astronomy. Since then, thousands of exoplanets have been confirmed, revealing an astonishing diversity of worlds, from hot Jupiters and super-Earths to cold gas giants and rocky, possibly Earth-like planets. Among these, those occupying the habitable zone are of special interest, as they represent the best candidates for hosting liquid water and possibly life. This report provides an in-depth overview of the current state of the search for habitable exoplanets, the scientific principles underlying exoplanet habitability, the detection techniques, major discoveries, challenges, future prospects, and the profound implications for humanity. Through a review of the latest research, missions, and theories, we aim to capture the excitement and significance of this remarkable scientific journey. 2. The concept of exoplanet habitability. 2.1. The habitable zone, definition and evolution. The habitable zone, HZ, is traditionally defined as the region around a star where a rocky planet with a suitable atmosphere could maintain liquid water on its surface, a necessary ingredient for all known forms of life. The concept, sometimes called the Goldilocks zone, is founded on planetary climate models that balance incoming stellar radiation with atmospheric effects. The classic habitable zone. The boundaries of the classic HZ are determined by inner edge, where a planet would undergo a runaway greenhouse effect, boiling away surface water, e.g., current Venus. Outer edge, where CO2 and other greenhouse gases can no longer prevent water from freezing, e.g., early Mars. This liquid water belt is not fixed. It changes as stars age and brighten. For a Sun-like star, the HZ is currently between about 0.95 and 1.37 astronomical units, AU. For smaller, cooler stars, the HZ is closer in, refining the habitable zone contemporary. Models take into account atmospheric composition. High CO2 or H2 atmospheres can extend the outer HZ. Planetary albedo. Cloud cover, ice, and continents can affect heat absorption. Stellar evolution. Stars brighten with age, moving the HZ outward. Geochemical cycles. Planets with active geology, e.g. plate tectonics, can stabilize climates over billions of years. 2.2 Planetary and stellar factors. Planetary factors influencing habitability. Mass and radius. Planets smaller than Mars may lose their atmospheres. Those larger than 1.5 Earth radii may develop thick, inhospitable envelopes. Magnetic field shields the surface from harmful cosmic rays and stellar winds. Geological activity drives carbon cycling and maintains long-term climate stability. Volatile inventory. Abundant water and essential molecules are prerequisites for habitability. Stellar influences, stellar type and luminosity, dictate the location and width of the HZ. Activity and flaring. Young stars and low-mass stars often exhibit strong magnetic activity, which can erode planetary atmospheres. Stellar multiplicity. Binary and multiple star systems can affect orbital stability and HZ dynamics. 2.3 Types of habitability beyond the Goldilocks zone. The search for life is expanding beyond the classic HZ, recognizing subsurface habitability, oceans beneath ice heated by tidal forces or radiogenic decay, for example, Europa, Enceladus, snowball and greenhouse planets, worlds that may be habitable under extreme atmospheric conditions. Tidally locked planets. Planets with one side facing their star may support life in twilight regions. Exomoons. Large moons orbiting gas giants within the HZ could be habitable. Astrobiology now considers a broad array of environments where life might arise. 3. Exoplanet detection, methods and milestones. 3.1. Transit Photometry. The transit method detects exoplanets by measuring the slight dimming of a star as a planet crosses its face. The depth, duration, and interval of the transit reveal. Planet radius, determined from the amount of light blocked. Orbital period and distance, calculated from the interval between transits. 2.3. Types of habitability beyond the Goldilocks zone. The search for life is expanding beyond the classic HZ, recognizing atmospheric properties inferred when starlight passes through the planet's atmosphere during transit, transmission spectroscopy. Space-based missions, Kepler, TESS have used this method to discover thousands of exoplanets. 3.2. Radial Velocity. The radial velocity method, Doppler spectroscopy, measures the star's wobble due to the gravitational pull of an orbiting planet. By analyzing shifts in the star's spectral lines, astronomers determine minimum planet mass, actual mass if inclination is known, orbital period, and eccentricity. This method is most sensitive to massive, close-in planets, but is increasingly able to detect Earth-mass planets with improved instrumentation. Examples: HARPS, Espresso. 3.3. Direct imaging. Direct imaging aims to separate the faint light of a planet from its bright host star. Techniques include coronagraphs, block out starlight to reveal nearby planets. Adaptive optics, correct for atmospheric distortion in ground-based telescopes. Infrared imaging, exploits the fact that young massive planets emit heat. Direct imaging is best for large, young planets far from their stars, but future telescopes, e.g. JWST, ELT, aim to image smaller, cooler worlds. 3.4. Gravitational microlensing and astrometry. Microlensing detects planets when a foreground star, with planets, passes in front of a background star, magnifying its light. Sensitive to planets at wider separations, including rogue planets. Astrometry measures tiny changes at a star's position in the sky, challenging but potentially powerful for nearby stars. 3.5. Emerging detection techniques. Timing variations, observing changes in pulsar, eclipse, or transit timing to infer additional planets. Polarimetry, analyzing polarized light scattered by planetary atmospheres or surfaces. Ongoing advances promise new ways to find and characterize exoplanets. 4. Major exoplanet surveys and missions. 4.1. Kepler and K2. The Kepler mission, 2009 to 2018, was the first to systematically search for Earth-sized planets in the habitable zones of Sun-like stars. Its fixed field of view monitored over 150,000 stars, yielding over 2,600 confirmed exoplanets and thousands more candidates. The first statistically robust estimate that planets are common and small rocky planets in the HZ might number in the billions in the Milky Way. K2, the extended mission, surveyed additional fields, increasing the diversity of targets. 4.2. TESS, Transiting Exoplanet Survey Satellite. TESS, launched 2018, is scanning nearly the entire sky, focusing on bright, nearby stars. Its goals include discovering small, transiting planets suitable for atmospheric characterization, enabling follow-up observations from ground and space. TESS has already identified thousands of planet candidates, including several in their star's HZ. 4.3. European missions, Cheops, Plato, Gaia, characterizes known exoplanets by high-precision photometry, refining their radii and densities. Plato, planned for 2026 plus, will search for transiting exoplanets around bright stars, focusing on habitability and system architectures. Gaia provides astrometric data, enabling discoveries of planets through tiny stellar motions. 4.4 Ground-based surveys and networks. HARPS, Carmenes, Espresso, high-precision spectrographs for radial velocity measurements. Me-Earth, SuperWASP, HatNet, networks of small telescopes monitoring thousands of stars for transits, especially M-dwarfs. These ground-based efforts complement space missions and enable rapid follow-up. 5. Cataloging habitable zone exoplanets. 5.1. Defining the habitable zone for catalogs. Catalogs use various criteria for inclusion as a habitable zone planet, often considering insolation, the amount of stellar energy received compared to Earth. Planet size, usually restricted to 0.5 to 2.0 Earth radii for likely rocky composition. Stellar properties, host star's luminosity, temperature, and activity. Databases such as the NASA Exoplanet Archive and the Habitable Exoplanets Catalog track these worlds. 5.2 Summary of known habitable zone exoplanets. As of 2025, dozens of confirmed exoplanets reside in the HZ, with hundreds of candidates. Most orbit M-dwarfs, though a growing number are found around K and G stars. Important examples include Kepler 186f, first Earth-sized planet in the HC, Kepler 452b, super-Earth in the HC of a G star, TRAPPIST 1e, F, and G, Earth-sized planets in the HZ of a CO, Proxima Centauri b, closest potentially habitable exoplanet, TOI 700d, first Earth-sized HC planet discovered by TESS. 5.3 Kepler's habitable zone candidates. Kepler's dataset remains a goldmine for HZ candidates. Analysis reveals the frequency of Earth-sized HZ planets NABS is likely 0.1 to 0.5 per Sun-like star. Many HZ candidates await confirmation via radial velocity or other means. 5.4 Other notable systems. TRAPPIST-1, Proxima Centauri, and more. TRAPPIST-1, 7 Earth-sized planets, 3 in the HC, allow for detailed comparative planetology. Proxima Centauri, its planet, though in the HC, is challenged by stellar flaring. LHS 1140, K2 18b, Ross 128b, all are within the HC of nearby M-dwarfs and are prime targets for atmospheric studies. 6. Habitable zone exoplanets, physical and environmental characteristics. 6.1 Planetary mass, radius, and types. Rocky planets, up to around 1.5 Earth radii, with densities suggesting silicate metal composition. Super-Earths, 1.5 to 2.0 Earth radii, possibly rocky or water-rich. Mini-Neptunes, larger planets with thick envelopes, less promising for surface habitability. Mass and radius together inform us about internal structure, surface gravity, and atmospheric retention. 6.2 Orbital dynamics and climate stability. Eccentricity. High eccentricity can drive extreme climate cycles. Resonances. Planets in multi-planet systems may experience stabilizing or destabilizing gravitational effects. Obliquity. Axial tilt, it's stable, can regulate climate and seasons, as on Earth. 6.3 Atmospheric retention and composition. Escape velocity. Determines ability to retain a substantial atmosphere. Outgassing and volcanism replenish atmospheric gases. Hydrogen loss. Light atmospheres are vulnerable to escape, especially around active stars. A planet's ability to maintain an atmosphere is critical for surface habitability. 7. Exoplanet atmospheres, climates, and surface conditions. 7.1 Methods of atmospheric characterization. Transmission spectroscopy. During transits, starlight filters through the atmosphere, revealing absorption lines. Emission spectroscopy. Observing the planet's own emitted infrared light, especially during secondary eclipses. Phase curves. Measuring brightness changes as a planet orbits inferring atmospheric dynamics and heat distribution. JWST and future telescopes are targeting HC exoplanets for such studies. 7.2. Signatures of habitability in surface environments. Water vapor, key indicator of potential surface oceans. Greenhouse gases, CO2, CH4, regulate planetary temperature. Oxygen and ozone, potential biosignatures, though can be produced abiotically. Clouds and hazes, affect both climate and detectability of surface features. 7.3. Tidal locking, spin states, and implications for life. Tidally locked planets have permanent day and night sides. Atmospheric circulation may transport heat, creating temperate zones. Substellar and terminator regions may offer stable, habitable conditions. Climate models suggest many tidally locked HZ planets could sustain life, though they may differ greatly from Earth. Searching for life. Biosignatures, technosignatures, and the limits of detection. 8.1. Biological and chemical biosignatures. Oxygen and ozone, byproducts of photosynthesis, accumulate only if not rapidly consumed by geology or chemistry. Methane, quickly destroyed in oxygen-rich atmospheres. Its persistence implies replenishment. N2O, CH3Cl, and other trace gases, produced by biological processes. Detection of biosignatures requires ruling out non-biological sources. 8.2. Spectroscopic markers and surface features. Vegetation red edge, a sharp increase in reflectance at around 700 nanometers due to chlorophyll. Seasonal variability. Changes in atmospheric composition or color could indicate life cycles. Polarization signatures. Life may produce distinctive patterns in polarized light. 8.3. Technosignatures, evidence for advanced civilizations. Radio and laser emissions sought by projects like SETI. Artificial night-side lighting, detectable as unusual light curves. Industrial pollutants, spectral lines from CFCs or other synthetic chemicals. No confirmed technosignatures have been detected to date, but searches continue. 8.4. False positives, abiotic sources, and ambiguities. Abiotic oxygen can accumulate via photodissociation of water and hydrogen escape. Volcanic or hydrothermal methane may be abundant on lifeless worlds. Planetary context. Understanding geology, stellar history, and atmospheric evolution is essential for interpretation. Careful modeling and multi-wavelength observations are needed to distinguish life from lifelike chemistry. 9. Challenges, biases, and open questions in habitability studies. 9.1. Observational biases and detection limits. Transit probability. Only a small fraction of planets transit from our viewpoint. Planet size and brightness. Larger planets and those around small stars are easier to detect. Distance and stellar noise. Fainter, more distant stars are harder to study in detail. These biases affect our understanding of the true frequency of habitable worlds. 9.2. Planetary and stellar evolution. Stellar aging. HZ migrates outward as stars brighten. Planetary cooling. Geological activity may cease over time, ending climate regulation. Stellar and planetary magnetic fields affect atmospheric retention and radiation environment. Long-term habitability requires stability over billions of years. 9.3. Alternative biochemistries and unconventional habitats. Non-water solvents. Life may arise in methane lakes, Titan, or in supercritical CO2. Silicon-based life, hypothetically possible, but chemically less versatile than carbon. Exotic energy sources. Life could be powered by chemical gradients, radiation, or tidal heating. Expanding the search beyond Earth-like life widens the possibilities, though detection becomes more challenging. 9.4. The Fermi paradox and the prevalence of life. The apparent contradiction between the high probability of habitable planets and the lack of evidence for life Fermi paradox prompts debate. Life is rare or fragile. Intelligent life is even rarer. Civilizations do not transmit or are short-lived. We are early, or detection methods are insufficient. Resolving these questions is a key motivation for ongoing research. 10. The influence of stellar types and system architectures. 10.1. Sun-like stars, G-dwarfs. Wide, stable HZs. Lower stellar activity compared to M-dwarfs. Long main sequence lifetimes, billions of years. Earth analogs are most likely to be found around G-dwarfs, though such systems are less common than M-dwarfs. 10.2. Red dwarfs and M-stars. Most common stars in the galaxy. Close-in HZ, leading to tidal locking. High stellar activity, especially in youth. Long lifespans, offering long windows for evolution. Most nearby HZ exoplanets are around M-dwarfs, despite their challenges. 10.3. K-dwarfs and orange dwarfs. Intermediate properties, stable, long-lived, less active than M-dwarfs. Potentially ideal for habitability. Underrepresented in current surveys, but expected to be fruitful targets. 10.4. Binary and multiple star systems. S-type, circumstellar, and P-type, circumbinary planets. Dynamical stability can allow HZs in many binaries. Complex illumination and climate patterns possible. Several circumbinary planets are known, though few in the HZ. 11. Future prospects, missions, technologies, and the road ahead. 11.1. Next-generation space observatories. James Webb Space Telescope, JWST. Infrared spectroscopy of exoplanet atmospheres, especially for nearby HZ planets. Roman Space Telescope. Microlensing survey for distant exoplanets. Aerial, dedicated to atmospheric characterization of exoplanets. 11.2. Ground-based giant telescopes. Extremely Large Telescope, ELT, 39 meters. Direct imaging and spectroscopy of small exoplanets. 30-meter telescope, TMT, and Giant Magellan Telescope, GMT. Similar capabilities, focusing on nearby stars. 11.3. Proposed and concept missions. LUVOIR, Large UV Optical IR Surveyor. Direct imaging and spectroscopy of Earth-like planets. HABEX, Habitable Exoplanet Observatory, focused on finding and studying habitable worlds. Starshades and interferometers, innovative designs for blocking starlight and improving contrast. 11.4. SETI, interstellar probes and long-term goals. Breakthrough Listen, largest SETI program to date, scanning for techno-signatures. Breakthrough Starshot, concept for sending gram-scale probes to Alpha Centauri at approximately 20% light speed. Solar Gravitational Lens, using the Sun's gravity as a massive telescope for imaging exoplanets. The future promises unprecedented capabilities for exploration and discovery. 12. Philosophical, cultural, and societal impacts. The transformative power of discovery. Finding life elsewhere would revolutionize biology, philosophy, religion, and our sense of place in the cosmos. Even the absence of life on myriad worlds would be a profound result, sharpening our appreciation for Earth's uniqueness. 12.2. Astrobiology and the cosmic perspective. Astrobiology encourages humility and interconnectedness, reminding us that life on Earth may be one example among many or a rare exception. 12.3. Ethics of exploration and contact. Planetary protection, avoiding contamination of other worlds. Ethical exploration, respecting hypothetical alien biospheres. Communication protocols, preparing for contact with extraterrestrial intelligence should it occur. 13. Conclusion. The quest to find habitable exoplanets and search for life beyond Earth is a scientific odyssey of unprecedented scope. In just a few decades, we have moved from speculation to discovery, and from discovery to detailed study. The habitable zones of other stars, once theoretical, are now populated with worlds whose properties we can measure and whose atmospheres we may soon analyze. Future missions and technological advances will expand the frontiers of exoplanet science, bringing us closer to answering the age-old question: are we alone? Whether we find evidence of life or not, the journey itself reshapes our understanding of the universe and our own existence. 14. References: Casting, J.F., Whitmire, D.P., and Reynolds, R.T. Habitable zones around main sequence stars. Icarus, 101, 1, 108-128. Seeger, S., 2013. Exoplanet Habitability. Science, 340-6132, 577-581. Baruki, W.J., et al., 2010. Kepler Planet Detection Mission, Introduction and First Results. Science, 327-5968, 977-980. Anglada Escude, G. et al., 2016. A terrestrial planet candidate in a temperate orbit around Proxima Centauri. Nature, 536-7617, 437-440. Gillen, M. et al., 2017. 7 temperate terrestrial planets around the nearby ultra-cool dwarf star TRAPPIST-1. Nature, 542-7642, 456-460. Meadows, V.S. et al., 2018. Exoplanet biosignatures. Understanding oxygen as a biosignature in the context of its environment. Astrobiology. Tartar, J. 2001. The Search for Extraterrestrial Intelligence, SETI. Annual Review of Astronomy and Astrophysics, 39, 511-548. Cockell, C.S. et al., 2016. Habitability, a Review. Astrobiology, 16, 1, 89-117. NASA Exoplanet Archive, https exoplanetarchive.ipac.caltech.edu. The Habitable Exoplanets Catalog, https phlupr.edu projects/Habitable Exoplanets Catalog. Barnes and et al., 2013. Tidal Venuses, Triggering a Climate Catastrophe via Tidal Heating. Astrobiology, 13:3, 225-250. Lingam, M., and Loeb, A., 2019. Physical Constraints on the Likelihood of Life on Exoplanets. Reviews of Modern Physics, 91-2-021-002. Thank you for watching. We hope you enjoyed today's video. If you did, don't forget to hit that like button and subscribe to our channel for more exciting content. Your support means the world to us. We can't wait to see you back here for our next adventure. If you have any feedback or ideas for future videos, drop them in the comments below. Until next time, take care and stay awesome. See you soon.